Hello everyone. In the one of the next episodes about the .NET GC internals, uh, this is the sixth one as far as I remember, and today we will cover the compact phase. I have a little different setup today, so probably something will be not working, but we will see. As I said, and as always, it is nice to see you all, so say hello from where you are, and hello Christoph, hello Laszlo, and there was a question how long this webinar will take today. I believe it will be around 1 hour. It is a little less complex topic, like it is complex, but maybe I will manage to get into a 1 hour webinar. And yes, I'm also hoping I'm recovering well, Christoph, so let's just proceed without the further delays. Compact phase is the one that we will cover today. And just to remind you the whole agenda, we are now probably somewhere in the middle. We have covered a lot, so we all know about mark, concurrent mark, plan, sweep, and today we will cover the compacting. So we have this plan phase that was described, which is pretty awesome, like it is doing a lot of awesome calculations that the GC is able to use later on. We have covered the sweep phase, and now compacting, something which is the second possibility how the GC can reclaim memory. So in general, the compacting is the concept that all no longer reachable objects should be simply compacted. So let just me switch to my magic pen. We have this after the mark phase. We have all this object graph being traversed, and we have marked objects that are alive. We have seen this graph many times. So also we know which are not reachable because we have not marked CNF. And the compacting will be something like we would probably think about reclaiming memory if the objects were Lego bricks. So if we have this continuous memory region, and we know that we don't need CNF anymore, we can simply move all the objects all together next to each other and get rid of the gaps. So some objects will not be moved because the ones at the beginning, as we see, will not be moved. Then we will be moving object by object, conceptually at least, to get rid of those objects that are no longer needed. So we will be simply overwriting, we can say like that, overwriting the memory after the objects that are no longer needed with the objects that are still reachable. So conceptually it looks like that. Okay, sorry for, but as I said, a new setup, so something I must get used to it. And as always, if you have any questions, do not hesitate to ask. I love questions, so if you have any questions, always you can interrupt me if something is not clear enough. So this compacting, this is how it looks in theory in every compacting GC in the world. This is the whole concept. And in terms of the .NET GC terminology that we already probably know after the previous episodes, it means that now in words and in the names of the .NET GC that the GC is using, we will move plugs around to produce compacted heap. Because we know in the end the GC groups reachable objects into so-called plugs, and then it will be not considering moving individual objects, but all plugs. Plug by plug, it will be trying to find a good place for a plug to produce compacted heap. So this plug concept is here important, and it is important to understand that from now there is nothing like individual object. We are considering the whole plugs, so grouped objects living next to each other which are still reachable. So the compacting is non-concurrent in the current GC in .NET. Because it is like that, it is not so trivial to introduce compacting concurrent GC. There are compacting concurrent GCs in the world. In Java world especially, we have even few possibilities, few GCs that are simply compacting while the application is running, which you may imagine is not trivial because we are compacting memory and objects while the application is using them, so it is not trivial for sure. And probably one of the reasons is like this is not yet implemented in .NET GC runtime, in the .NET GC. It will be eventually for sure. Now the focus is on different features and improving the current implementations instead of jumping to this algorithm for concurrent compacting in case of .NET GC. So we have non-concurrent compacting on the only one possibility, and so we are going and returning to this graph describing how the GC is inside working. We know that the garbage collector will be called at some point in time because of the probable allocations. We will decide which generation should be condemned, which means which generation will be garbage collected, and then if there is decision to go into non-concurrent, so stop the way of working, there will be this mark phase, non-concurrent mark phase obviously, and the plan phase, which we have covered in fourth episode as far as I remember. And this plan phase is pretty sophisticated, as you I hope remember, because it is calculating without moving anything, and in fact almost without doing any memory accesses, almost. It is calculating information both for sweep that we have covered last week and for compacting, virtually kind of. So it is now in full knowledge whether the compacting will be beneficial or not. So there is this method called decide on compacting, which is deciding whether now it is a good point in time to compact. And if it will be compacting, there is the compacting happening in non-concurrent manner. Those two methods will be called and other bookkeeping. And today we will cover those ones. So we have covered all this before. So we have covered mark phase, plan phase, and today we are going on this part of the graph. What is important from this point of view is that the current compacting in .NET GC happens after the mark and plan phases. So we are after the plan phase. We know all this data that will have been described in the plan phase. We know the plugs, we know the gaps. We have this old data gathered in brick tables and plug trees and so on and so on. We are after the plan phase. So the compact phase, when looking at it, is conceptually consisting of two main phases, obvious ones we can say. The first one is that obviously we need to move objects, copy them from there to there, from here to there, to compact memory. And as we know, we will be talking about probably moving whole plugs, not individual objects, and then updating all references between objects, because we have moved objects and some references were pointing to those objects, so we need to update all those references. And it is pretty complex, like a lot of operations. Imagine, and let's make a few drawings. Imagine that this object has, maybe I will change the color. Imagine that this object has a A has a reference to C. It cannot have because it is not. A has reference to D, and A has reference to G, and so on and so on. So the first phase would be to move those objects. So this is the first phase. But also we need to update after moving those objects. At least the result needs to be that this reference from A to D needs to be updated because it is now pointing to a different point in memory. And the same for A, because A okay, that's not good because you don't see what I'm drawing. And as I said, that's not good because I've changed the setup. So let's just, okay, I know why. Fast debugging. I need to change one thing. I will share the whole change the whole. I will share. Yeah, as expected, there is problem. Okay, that's the funny point when you see. Okay. I'm simply using single monitor, which complicates thing a lot. I really love to have two monitors, but currently I don't have. So now you should see the drawings. So we have this object. Thank you for pointing that out. A has a reference to D and A has a reference to G. And after we have moved all those objects, we need to update obviously those references. So we simply need to go object by object and see, okay, A has a reference to D, but D has been moved. So we are updating this reference and we are now saying the reference points to this address. Then the same for B, D, A, we will see that it has an outgoing reference to G. So now we need to calculate what's the new position of G to update this outgoing reference. So you can imagine that it is a lot of calculations because we have many references between objects and we need to update them all. So this is pretty a lot of things to do. How it is implemented, I will just describe in a few seconds. A lot of updating. And both operations can be treated as pretty complex because first of all we need to move those objects around, so we are introducing pretty big memory traffic, and then all those calculations to update references also is a huge amount of work. So those are the overheads of compacting. I will hide this. I don't know if I can hide this, so I will just move it somewhere here. Okay. In the end, I described it in that order, but it is wise to do it in an opposite order. So first of all, we will update references in objects. And this is wise because we know where they are, so we can go object by object. Every reachable object, we know what it is because we have plug info. And we know where it will be moved because of the plan phase has introduced this reallocation offset for every plug. So we know for every object, living object, where it will be moved. So we have the full information. So we can go object by object, update the references, and only then move the objects itself. Sounds good. With all those updated references. So if you would draw this somehow, we will see that the beginning is that A was pointing to D, and here it is the case. And then the second, the intermediate state would be that there would be A, B, C, D, A. I don't know if I'm spelling the alphabet correctly. So we will see that this is the one step, the beginning. The first step would be to update the references. So we will go object by object and see that, okay, this object has an outgoing reference to D. And because of the plug info from the plan phase, we know where the DB will be moved. So we'll be just updating this reference to a proper address. Then we will go B doesn't have outgoing references, C should be ignored because it is not reachable, D has no references, A has a reference to G, and we know where the G will be allocated, so we will update the reference somewhere here probably, because it will be just we know where will be what will be the future address of G, and so on and so on. So this is the reallocation phase, and then only then we will produce the final result. So we will have A, B, C, and so on, pointing to D. No. Oh my God, no. Okay, A, B, D, D, A, and G. Ad hoc drawing, which is not perfect, but and in the end it is almost correct. Like I didn't manage to draw it properly, but all those references are there and they are correct because we have set it to have proper future addresses and we have a correct managed heap in the end. I hope it is clear. I at least tried to explain it in a simple words. So that's the whole concept. At the first phase, at the first stage, we are updating our references, and in the second stage, we are moving all objects. And that's why we are seeing here in the opposite order. The first is the reallocation phase, calculating all those outgoing references, and only then compacting phase. So let's look at those two phases in details. The reallocation phase, reallocating references. We have an object. Let's concentrate on a single object because we are probably in a plug, and then we are considering objects in a plug. And we are now interested in knowing what will be the future references inside an object. So imagine we have an object somewhere called X, and it has a reference as a field, and it is pointing, let's say, to an object which is living somewhere here. And now we would like to reallocate, so recalculate out all outgoing references from X. Obviously JIT metadata knows where are the outgoing references from objects, so GC knows the offsets of outgoing references. So when considering this particular object, it will know that, okay, at this offset there is an outgoing reference, and it's because reference in the end is just a pointer, it is pointing to this memory address. And how to calculate the future address of this reference? Obviously, we need to use the information from the brick table and plug tree. So by simple dividing this address of this reference, which is pointed by this object of this point by this reference, we will divide it by the size of brick entries. We will know which brick entry contains this object. Then we will traverse the plug tree to find proper plug. So we will start from the root. Then we will see that okay, root is too small, so we will go to the right to this one. So we will visit at this one, and in the end we will end with our plug. And then we have the plug info, and inside every plug info, as we probably remember, there is a reallocation offset, which means there is minus or plus offset, and that's all. We know that this whole plug will be moved somewhere by this offset. So just dividing this address, subtracting this address with this offset, will produce the future address, and that's all. That's the update of the reference, of outgoing reference. So with the help of the plug info and with the help of traversing the plug tree, starting from a brick table entry, we are calculating future addresses of every object that will be moved. If the allocation address is if the allocation offset is 0, it means that this particular plug will not be moved. So the plan phase calculated that this particular plug will not be moved. But we don't know whether it will be moved or not, so we need to traverse the whole plug tree to find this information that, for example, this particular reference will be not updated because the allocation offset is 0. A lot of accesses to this tree, because for every reference we will need to traverse one plug tree in a particular brick table to find this reallocation offset. Again, a lot of calculations. And that's the reallocation phase. If you have any questions, do not hesitate to ask. So we need to update all references. I mean, many places needs to be scanned because many places can contain references to objects. So just to point out as much work needs to be done, let's just list all those places that we need to scan to update all the references. So first of all, during this reallocation phase, and as you remember, all this is happening in non-concurrent manner, so we don't care about anything because the application is paused, so we don't need to be worried that something will be moved or invalidated. So first of all, we need to update all references on the stack. So we need to scan all managed threads, and stack by stack, frame by frame, every reference that we have on all threads needs to be updated with the help of the algorithm that I described. Then, so as a lot of threads incurs a lot of work here because we have probably a lot of references to update. There is also something which is called cross-generational remembered set. I will cover that next week because I will cover generations next week. We need to track some references that are between generations. They are called remembered sets. And they are references because there is a set of references that are cross-generational, but they are still references. So we need to update objects that are there, and all references that are in those objects needs to be updated again. Obviously, all references inside reachable survived objects in small object heap. So every object in the small object heap needs to be scanned plug by plug, brick by brick, and to do exactly what I described. So we will be just doing we have a brick entry. With the help of the bricks and plugs, we know where there are living survived objects. So then plug by plug, we will be just doing exactly that. We will start, for example, from the first one, so from the root, and object by object, we will then consider whether objects there have outgoing references or not, and update them update them simply, because we then need to do all those calculations. Then we will move to this plug, and then because all the living objects, all objects are living, so again, object by object inside this plug, we will update all outgoing references in this plug. And to the left and to the right, every plug inside the particular brick will be updated. Every reference that is from there outgoing somewhere will be after this simply recalculated. That's the whole story. A lot of work, as you can imagine. Okay. Question. I need to switch to StreamYard to show the question, which is unfortunate, but I don't know how to do it better. And I don't see the question. That's really strange. So I will do it like that, sorry for inconvenience. What about the references on stack in the memory? Yeah. So references on the stack generally are the one that local variables. Yes, those, what I meant by updating and scanning the managed stack frames is exactly about that. So references on the stack means runtime provides this information to the GC, saying that okay, I have a thread number 1, and this thread has 3 stack frames. This is on the top, but there are some below, and with the help of the runtime, the GC will be reported that these particular addresses on the stack are references, so local variables that are references pointing somewhere, and they will be updated because the runtime will provide this information and enumerate all the references, and the callback doing all this recalculation will be handled by the GC. So stack thread by thread, frame by frame, all local variables which are references will be updated in that way. I hope this answers your question. If not, do not hesitate to ask again in different words, or maybe some more clarification is needed. So small object heap uses the information from the plan phase, which is heavily based on plugs, and on large object heap the same story, but as you probably, I hope, remember, the large object heap tremendously often is non-compacting, so there is no plan phase for it. We don't have plug informations on large object heap, so then simply object by object scanning is happening. Something very similar like here. We are just scanning object by object on large object heap, checking whether there are outgoing references in every particular object and updating those outgoing references. If you have an array of strings, it means you have whole bunch of references, outgoing references, because an array of strings is simply array of the outgoing references to strings. What needs to be done, if you remember plan phase, there was a concept of pre and post plugs. So for a plan phase time, we were destroying parts of an object to put it on the side for a moment to store the plug info, and we were destroying simply parts of an object which is still living, and we were calling it pre and post plug. And because there is those pre and post plugs are parts of objects, they can contain references, so we need to update references inside those pre and post plugs. It is just kept somewhere on the side that we need to traverse all those pre-post plugs and update them the same manner as I described. Then finalization queue is full of references. So I mean, finalization queue may contain objects. I mean the f-reachable queue, which is of objects that are going to be finalized, let's say, and they obviously this is just a queue of objects, and those objects may contain references, so we need to go object by object inside finalization queue and update all references there. Also, handles as one of the type of the roots are keeping objects alive, like statics, for example, and so on and so on. We'll cover that in the one of the next episodes about the roots. And so handles are pretty important and sources of roots, so we need to go through handles and see what they are pointing to, and if those objects pointed by handle contains outgoing references, the same story, it needs to be updated reference by reference. So in the end, we have a lot of places that with the help of the runtime, GC is scanning, and for every outgoing reference is doing this calculation. Typically, the most of the work is happening here because we can have a lot of objects on a small object heap. So this optimization with the help of plug tree is pretty nice because we have this binary tree access time for scanning this information. And probably we can expect some at least references on the stack, but it all depends what you are using and what your code looks like, how many threads you have, and so on and so on. And there will be the main two places when the most of the work is happening. A lot of work again, as you see. Then compacting. So I hope I covered the reallocation phase. We know how the outgoing reference is being updated. We know where we are looking for those outgoing references. So after this reallocation phase, now we have the full correct future state of objects. Every object now has the references that are pointing to future addresses after compaction. That's nice. So the only one thing is left now. We need to move those objects. We have outgoing references updated. Now we need to move those objects. And this is happening plug by plug. Because as we know, every plug has this information about the reallocation phase. So it is pretty simply. I like maybe this nothing is simple in GC, but we can say that conceptually at least it is pretty straightforward. So we have a plug, and for every plug there is this gap plug pair info. Every plug has information calculated during the plan phase. What's its reallocation address? So for every plug we have this information, and then we simply go plug by plug and move those plugs. So starting from this plug, we will see, okay, this plug should be moved by 24 bytes. We will copy memory region of this plug to this, moving all the memory by 24 bytes. Then we go to this plug and we see, okay, this plug should be moved by 80 bytes. So we know that this plug, which is here, should be moved by 80 bytes. Again, we copy this memory. And for pin plug, the reallocation phase offset is 0. So this is not surprising, and this is how the pinning is handled. Simply it is just marked as pinned, and additionally this reallocation offset is 0, so we skip it. And then the next plug, the allocation offset is 160. Then we know that all this plug needs to be again copied by 160 bytes, and so on and so on, plug by plug. Those plugs might be pretty big because here I'm just showing you plugs consisting of few objects, but remember that plug may be in megabytes, even in gigabytes if you have a lot of objects. So few hundred megabyte of data may be moved with respect to this reallocation offset, and the whole plug will be moved like that to make this compaction. And this will be happening plug by plug. I'm seeing some questions, so I need to make this unfortunate switch to the StreamYard panel and just display the question like that, which is really strange. I need to do that like that, but sorry for that. I will find a better way next time. So Chris, you mentioned that the runtime is providing the outgoing references, but how to set the new addresses of these outgoing references? It is a pointer to a pointer that this callback is giving from the runtime to the GC. So you can simply have an address which is address, like you know. The GC is having the callback from the runtime, which is just pointing where is this reference, so you can update it simply. And I hope it answers your question. It is just pointer to a pointer that this GC callback is receiving. I don't know why I cannot. Yes, we are drawing a fractal here, which is pretty funny, but okay. Next question. What happens if, for example, the reference was put in CPU register? This callback provided by the runtime is also giving information about CPU registers. So the GC is aware of all the state of every thread in general, because remember, every thread is postponed, so we have this frozen state of every thread, and this context of the thread as it was running on the CPU is also stored, so this information may be provided by the runtime. So again, answering the second part, this register, as it is, the GC knows, because the runtime has provided it this information that this register is a reference, then it needs to be updated. And no, sorry, this is super nice question. So really internal one, but this whole episode and all this mini series is about super internal deep stuff. So really nice question. I probably should mention it by myself. We need to update a lot of things during the compaction. Like, for example, if you remember, write watch lists and other stuff that may be happening because there is a concurrent GC happening, which is now postponed, and we are just kicking in with the compacting GC during it. A lot of things maybe has to be changed because objects are moved around. So yes, we need to update a lot of things like mark array and pinned heap. Regarding pinned heap, there is a limitation. We currently cannot allocate objects on pinned object heap that have outgoing references. In the runtime, there is a flag and it is supported, but it is disabled, and we cannot allocate objects which have ongoing references in pinned object heap, which means pinned object heap is simply ignored during that, because we know there are no objects that were containing references. There is this call GC, I don't remember the class, but the name of the method is reference or contain references, and if this is true, the GC is not allowing you to allocate on the pinned object heap. Yes, I love I also love this. Like, I don't know how to solve it, and I don't want to waste your time, so I'm just doing this in this pretty idiotic way, but at least it works. Okay, so let's just continue. Again, do not hesitate to ask more questions, more deep questions. So we have covered this part. We said that we are moving plug by plug, copying this memory. So this is pretty simple. And obviously we need also to restore those pre and post plugs, because we have destroyed our living objects. As we see, we have overwritten the end of the plug with some pinned plug data, and we have stored elsewhere the real true data of this object. So after this, we need to restore this data and to restore it to the proper form of this object, to not destroy the data. So we need to restore all the pre and post plugs from the on the side collection. Okay, then the question I see, and again my magic from StreamYard. This is a sort of confirmation, but does this happens parallelly on all heaps at the same time? Yes. Yes, it is. It may be. It may. It is. I mean, the whole plan phase produces the data on the heap, so we have all this data that we need on the heap, like here or here or here. So this is like data that may be used by during the allocation, during this compaction phase. And now it really depends on the mode. If it is workstation DC, there is only one managed heap. If there is a server DC, we may have multiple heaps, by default as many as logical cores on the machine. So then all what I'm saying here is happening in parallel. So the compaction of every managed heap is done by a separate thread, GC thread, and ideally on the separate logical core, so it is truly a parallelized work, and this compaction is then happening in parallel. If it answers your question, or if you're not, just do not hesitate to ask more. So as you see, pretty a lot of memory traffic, because now we will be moving megabytes of data. Like if this plug at the end, for example, is 1 gigabyte, because we may imagine that we have 1 gigabyte of continuous reachable objects, we need to copy 1 gigabyte of data by few bytes. No, probably will not happen, but yes, we will need to move all this 1 gigabyte of plug by some offset. A lot of memory traffic. That's why compaction is an overhead. It has a lot of things to do, and that's why it is preferred to sweep and not to compact all the time, because probably you see that there is an overhead, and this decision to make the compaction, although it produces nice results without fragmentation, it is not trivial because it has its own cost. Copying objects by object or plug by plug. How it is happening? So you can imagine that, okay, I have 1 gigabyte of plug or 100 megabytes of plug, let's say, and we need to copy it by 1 megabyte. So it is pretty confusing for some people, maybe, that we have 100 of megabyte of data and then we are just moving it by 1 megabyte. So it looks like we will be at least at some point in time overwriting ourselves or so, because it is how it is happening. We could imagine that it is implemented by moving it to some temporary buffer. So for example, we would be copying the whole 100 megabyte of plug to some place and then move it again to the destination, but obviously it would be very inefficient. So it is not like that. And object is not a Lego brick. It may be moved in parts. We don't need to move the whole memory at once or so. We can copy paste it byte by byte, for example, and this is exactly what is happening. So this is the procedure used by the compacting GC. It is simply called Memcopy, and it is just copying memory by default in groups of 4-pointed sized regions. So every 4-pointed sized regions, one by one, we are copying it from the source to the destination. And we are doing this simply in those batches. Then obviously there may be some padding that it is not rounded to 4-pointed size regions. So at the end we will be also copy remaining, for example in 64-bit scenario, the remaining 16 or 8 bytes. But this in the end produces pretty efficient assembly, which we'll be just using as far as remember move instructions or any other efficient way of copying memory. So because of this grouping, this resulting assembly code is pretty efficient. So we are we are copying them in those packages, let's say, which are 4 pointer size regions. And because pointer size is 8 bytes, it means it will be for 32 bytes batch, copied one by one. As far as I hope I'm calculated it correctly. So this is the main routine used by this, and the whole hundred of or gigabytes of data will be eventually copied with the help of this particular routine inside the GC-CPP file code. And that's all. Like, almost everything has been covered. So we have done those two phases. We have reallocated every outgoing reference. We updated all outgoing references all over the place. And then the compacting phase. So we have just move objects around. And as we know, it is about plugs, not objects, which reduces a little bit the flexibility, because probably if we will be considering single objects, we could fit things better because it is just more flexible. So because of pinning or other stuff, there may be a reduced flexibility, and then probably if we have a plug, it is less flexible because we may not fit it inside a gap or before a pinned plug. Otherwise, if it would be a single object or few objects, probably we could fit them in smaller gaps. But this is a compromise that we need to live with, as we see calculations of those references that are so often and so problematic that having plugs is still beneficial, although it may reduce flexibility of moving objects around a little bit. So those two main phases are happening, and then we have a lot of bookkeeping. Like, for example, we will fix generation boundaries, and this is pretty important thing that I will cover next week about generations, because now we have moved all the objects and plugs, and we need to recalculate, okay, but when in the end are all our generations and starting, and other bookkeeping. Like I said, pretty a lot of data is interested about objects, and when we fixed and moved generation boundaries, probably it also incurs updating other things, because now the generation boundaries has been changed, so maybe cross-generational sets are not valid, and so on and so on. So some bookkeeping, heavy bookkeeping is happening here also. And at the end, pretty important and nice step, we can decommit some memory, because we have compacted our space. So probably there is a bigger or smaller free space at the end of so-called segment. So the physical representation of the managed heap. So it is now good time to decommit it, because it is our goal. Like our process would like to use less memory, and to make it happen, we need to decommit memory. So to return this memory to an operating system. And after compaction, there is a perfect place for that. We have freed some memory at the end of the segment, and then it can be returned to operating system. And this really reduces the memory usage. So imagine that you have, imagine that we have this segment that it contains some living objects here and there. In the end, there were our plugs, and after let's say here, and after compaction, the result is that it will be something like that. So we have compacted our own memory and copied our plugs, and now we have this free space at the end, and it is still obviously committed because we are just we're moving objects around, and whole managed heap is untouched. So to make this happen, that okay, our process really is benefiting, there is such a word, that memory has been moved and this space is no longer needed, we can decommit at least part of it, and we really reduced the memory usage of our process by this memory amount of memory. So this is pretty nice and big benefit of compaction. Also, obviously there is no fragmentation because everything has been compacted. If there are no pinned plugs, because pinning obviously reduces our flexibility, as I said. So if we have our let's say scenario that we have a plug here. Let's just, I hope I will draw it correctly, and we have pinned plugged here, so it is pinned and we cannot move it. And when for example we have another plug here, so now we have this problem of reduced flexibility because we would like to compact this memory, but we don't have a lot of possible moves. This one will be not moved because there is no need for that. This one cannot be moved because it is pinned, so we are just leaving those two plugs untouched, and this one will not fit inside this free space before a pinned plug. So because we are still considering the whole plug, we are not splitting it, we can move it only by this amount of memory. Let's say we have this scenario, so we will move it by a little bit, much less that, for example, would split it and put it part of it here and part here. We are just moving it by this smaller amount of possible memory. Then this one will be moved here also, and we will decommit the end of the segment. Pretty ugly drawing. Sorry for that, but my drawing skills are not perfect, unfortunately. Okay, I'm seeing some questions, so let's switch to our infinite mirror and see what you are asking about. During compacting on 30-bit larger double arrays are aligned to 8 bytes. Yes, in general there is a lot of alignment related code in the GC, so we will see that the GC is aware of alignment. So if there is a compaction in large object heap and it knows that this particular plug requires a specific alignment, it will be considered during the plan phase first of all, and then in the end it will be with the proper alignment also after the compaction. So yes, GC is aware during the planning phase about that. The second question, Gen 0 and Gen 1 is on ephemeral segment. Yes. We cannot return that to the operating system right only from Gen 2. Or there is a use case where we can return the ephemeral segment to the operating system as well. So yes, we are covering here a little bit of the physical representation of the managed heap, and more of it will be covered next week. But probably I will try to explain it still. So ephemeral segment, it is called ephemeral segment, is the one that contains Gen 0 and 1, and there is only one in case of workstation GC and as many as logical cores in server GC that contains Gen 0 and 1. And yes, at the beginning we can say that there is a generation 1, generation 2, 1 and 0 at the same segment, so after compaction part of it could be decommitted because it is just from the left to the right. So still we could decommit things, like with after compaction the gen it would like something like that. So gen 2 has been we can even say that in the ideal situation gen 0 should be empty after so let's draw it like that. And now gen 0 probably may be empty after compaction, but we could, if the even if the gen 0 is empty here, we could decommit part of the ephemeral segment. But GC in .NET currently is not doing that, because we treat ephemeral segment as something very volatile. A lot of objects are there, they are dying, then a lot of objects will be allocated. We don't know in the end what is a good size, how many memory we should decommit. So we don't decommit ephemeral segment, simply because we believe even if we have used part of it, in the nearest future we will be still interested in consuming part of it again, so we would need to commit those pages again. So to not overhead of constantly decommitting and committing memory, ephemeral segment is not decommitted. The other story for Gen 2, so there are after some time there are segments only with generation 2, so then we can decommit part of it, obviously, because if there is a segment with generation 2 with some free spaces here and there, after the compaction it may look that it contains only compacted part, and then we can decommit part of this segment which contains only generation 2. I hope it answers your question. As always, let's look at the questions, because I see there are some comments or questions. So Laszlo, let's just give me a feedback whether it explains this your question or not. And what is the size of the decommit unit? We are decommitting on the base of pages. So we will decommit pages, which is 4 kilobytes. I'm always saying here, I'm not sure whether it is 8 kilobytes or 4 kilobytes, but I believe it is 4 kilobyte, right? Yep. So this is our decommit unit, and the whole decision of the GC is how much you should decommit. I don't remember now the heuristics. It is somehow we are not decommitting everything, probably because if the memory was used even in Gen 2 segment, we expect at least part of it probably will be again used, so we probably decommit part of it, but I don't remember exact heuristics. Maybe around 80%. I don't remember. And so yes, so we decommit part of the segments, and that's right. We could return the full segment to the operating system if we decommitted all the memory from it. It may happen. So again, one more scenario. Imagine that you have a Gen 2 segment and there were some gaps, but most of it, not gaps. There were only few living objects. After some time, all of them are no longer needed, so we end up with a segment that does not contain any living objects, and it may be happening after compaction or even after sweeping. It may end up with this scenario that it is just empty. And now the question is whether we should decommit whole segment and return it to a operating system or not. And it depends. There is this technique which is called harding, which is just about not returning segments for the operating system, because if we have gathered some segment from the operating system, we believe that it is good that we have it. Probably it will be reused. So instead of returning it completely, like even not completely, like we have the committed it, but it is still reserved, but we may even return it to the operating system, so it will not reserved. And it's one of the possibilities. The second possibility is that we will not do that. We will just decommit this whole segment, so it will be decommitted. The memory will be not used and treated as a physical memory, but it is just still reserved for us, and we keep it in a to reuse list of segments. So we have this to reuse list of segments because we believe maybe in the future we will have this memory region, we will be reusing this memory region, so we have to reuse list of segments that again can be committed, and this memory region is still reserved. This was particularly important for 42-bit scenarios when the whole virtual address space is pretty limited, so there was a problem of fragmentation. So once we gathered some space from the operating system and we have reserved it, we were afraid of returning it because maybe in future there will be no possibility to have the same region because there is a fragmentation of virtual address space, virtual memory. So it was problematic in 32-bit. And in case of 64-bit, the virtual address space is so huge that we are not so concerned about that. Probably there will be always big enough. It is hard to imagine to not have possibility to commit a segment from virtual space in case of 64-bit machine, 64-bit runtime. This was used in 32-bit runtime, especially in case of ASP.NET, when they were expecting they are long running, and the resulting fragmentation of virtual space could be problematic. So this flag was enabled by default for ASP.NET. We could also enable or disable it by startup flag or other configuration. Okay, that's the story, and in the end we have this additional bookkeeping of a lot of things, because we have invalidated a generation size, boundaries and so on. So pretty a lot of additional bookkeeping, super internal things that I will rather like not to cover because they are not so super important. And that was all about small object heap. In case of large object heap, as you remember, there is no by default compaction. We may trigger compacting large object heap with the help of one of the flags. Recently also there is a possibility that the GC will trigger compaction of large object heap in the special circumstances. So large object heap compacting is pretty rare, but it may happen, even for example if we have triggered it manually. So if it is triggered and the large object heap compacting is happening, we are doing it before small object heap compacting, and there we are simply scan our objects which are marked and copy them one after another with the help of this data that we have gathered after the plan phase for large object heap, because large object heap was calculated. Plan for large object heap also is happening if we have triggered compacting of large object heap, obviously. And that's all. It's exactly the same algorithm, so object by object, but here we have those pretty big objects. They will be moved Y-ban1 with the respect of this reallocation offset that has been calculated for every object in this case. Before every object we have this space for a plug for the object info, and the allocation offset is one of the information stored there, and then copied one by one to the proper place, with one difference about pinning, because as you may remember, large object heap is like 99 and many nines after that % using sweeping. When we allocate an object inside large object heap, we expect this allocation will happen with the help of free space that we have there. So we are really interested in the free space in large object heap. So if there is a pinned plug, sorry, not plug, but pinned object inside large object heap, there is additional info stored for every pinned object in large object heap. What will be the length of the free space before it if we decide on compacting? And because we have decided on compacting, then we have this information, and we will just create a free space. So free item list will be threaded here with the size that has been calculated during the plan phase. So we have just create, because obviously pinning may introduce this fragmentation, some free space may be created because of that. We will just thread this information into the free item list, and we will gather this and remember that, okay, because of the compaction, now we have a free space of the size 56 at this particular place. And this is exactly how it works for the sweeping. We have covered creating and handling free items in the previous episode. This is made in exactly the same manner. There is a free space list of free spaces on large object heap, and we are simply adding information about this particular gap created because of the pinned object before it, and we are adding this to the whole information about list in large object heap. So large object heap has a little different handling because of that. We are just interested in storing the information about the resulting free space. And that's all. That's the whole compacting happening here. We have covered both phases that are sub-phases of the compacting. If you would like to see the code, it is pretty simple, we could say. Like the complexity of the compacting relies mostly on the fact that it is just reusing all the information that we have gathered previously. So we need to understand the plugs, the plan phase, bricks, all that stuff that we need to understand what is happening here in compacting. But the whole compacting code is pretty straightforward if you understand all those previously described topics. So there is a reallocation phase which updates all those references, addresses to moved objects, and then compacting phase, which will traverse plug tree brick by brick and call this method compacting brick, and in the end inside compact plug, which is just for moving particular plugs with the respect of this data that we have calculated with respect to the reallocation offset. Okay. And that's all. That's all. If you are interested in the source code, you have those 4 methods to start from. Don't be scared in the amount of bookkeeping that is down there, because a lot of data needs to be updated also, but the concept is like I described. So slowly ending. I hope I explained it a little, at least in details, how this compacting is happening. Now it is a perfect time for questions, because it is like the last minute before I will end for today. And next week we will cover generations. So we have started part of it to cover today, because what I said so far doesn't touch the topic of generations. So we could imagine a whole managed heap treated as a whole with the respect of all these algorithms. But then we have that optimization in form of generations, so I will cover what they are, how they are implemented. To explain that also I need to explain a little bit of physical organization, so we will cover segments. Other interesting topics like card tables will be covered about generations. The question is whether Gen 0 and Gen 1 are always compacting. No, because it is, as you saw, a lot of work to do. So it is always a decision based mostly on fragmentation. So while Gen 0 and Gen 1 are always non-concurrent, that's true, they are sometimes compacting, but mostly sweeping. And this is all the dance around the heuristics, whether it is now worth to compact or maybe sweepings will be still good enough. And then wait for the bigger fragmentation that will trigger compacting. So I answered a little bit, and mostly it is about fragmentation. So if obviously the GC tracks all the time what is the resulting fragmentation, how many free spaces we have, what is the reusage of this free space, whether we are those gaps that are created are good for using for allocations or maybe totally not, whether this fragmentation is severe enough that probably now it is just the only thing that we can do is to compact to make things better, to get rid of those gaps and start from the beginning, start all over again. Okay, does the commit behavior retain VM setting? I don't remember. Let's retain. Oh no, no Epic Games. Retain VM. Retain VM. Okay, so it is called retain VM. Yeah, this is the one. Internally it is called hoarding, and as far as I remember it was called like that in the full framework, at least at some point in time. Now we have this retain VM, which is just to put on standby list the segments that otherwise would be decommitted, sorry, right. Let's look if we have another questions. If not, we will cover generations next week. A super interesting topic as all topics here. So thank you for watching, thank you for asking. I love questions, so especially if they are just allows to see things from a different angle that I prepared. So thank you very much for listening to me. See you next week. Stay tuned on Twitter for other how it is called. I don't remember now how it is called, for the reminder about the next webinar, and see you next week then. Have a nice evening or morning, depending where are you currently. And let's just switch me to the one and broadcast. Bye. This infinite screen needs to be fixed for sure. Bye. Thank you.